Hello everyone, welcome to Kepler. Today we will be discussing the problems for the contest, Codeforces contest. Hello, 2026. This was the first contest for this year, and it had a lot of interesting problems to discuss. So let's jump into the first problem. For the first problem, it is a binary array game. So basically, Alice and Bob play a game on an array of integers of size n, consisting of numbers 0 and 1, and basically each move is as follows. In each turn, the player must choose two integers L and R such that L is less than R, and then the subarray A of L to R is replaced with a single integer 1 minus minimum of A of L to R. So basically, if all the numbers in the subarray are 1, then the minimum value is 1 and the replaced value becomes 0. Otherwise, if there's any 0 in the array, in the subarray, then the value becomes 1. Right? So basically, this game is continued until we end up with a single integer remaining in the array. Alice wins if the final number is 0. Otherwise, Bob wins. Great. So let's perform some observations on this. Uh, so the operation can be summarized as follows. We select a subarray A of L to R and convert this to a value X, right? If 0 belongs to A of L to R, then X is 1. Otherwise, X is otherwise X is 0. Okay. So if all the values are 1 in the subarray, then the replaced value is 0. Now assume 0 does not belong to A, okay? So basically something like A equal to several ones, right? In this case, we can just select the entire array A of 1 to n and convert this to a single tier 0. Because since there are no zeros in the entire array, we can just select the entire array and change this to a 0 value. So in this case, Alice directly wins. Okay. Now, if 0 belongs to uh, if 0 belongs to the array, that implies uh, if we perform the operation on the entire array, we get the value 1. Like, since there is a 0 in the array, the minimum value is 0. So the replaced value is 1 minus 0 equals 1. So if Bob had this array given already with a 0 present in the array, in this case, Bob will win. Right? So we cannot let Bob have an array which has a 0 in it. On the other hand, if Bob has an array with only ones in it, he will be forced to make the only move, which is to uh, uh, take some 0 ones and convert it to a 0. So basically, what this comes down to is uh, so basically, suppose in the initial array, uh, 0 does not belong to uh, A in the initial array, then just perform uh, operation on entire array, right? And Alice wins. Otherwise, you have to remove all zeros from the array. Because if any zeros are left over in the array and given to Bob, Bob will just take the entire array and convert it to 1 and win the game. So Alice must remove all the zeros from the array before handing it over to Bob. So this means that the operation must be such that all zeros belong to A of L to R in Alice's move. Okay. So suppose L0 is the first occurrence uh, of 0 in A. R0 is last occurrence of 0. Then the operation is just remove A of L0, comma R0. Right. So this was an example. If you look at some of the test cases we had, uh, yes. So if you have something like A equal to 1 comma 1 comma 0, Alice will first take this small part, and this essentially removes the zeros, all the zeros in the array. So we get 1 comma 1, and Bob can make the only move in this array and convert this to a 0, and Alice will win. Okay, but there is a problem edge case here. If it was something like 0 1 0, in order to remove all the zeros from the array, Alice must choose the entire array itself. But this converts it to a value 1. In this case, Bob wins, right? So if L0 is equal to uh, 0 or 1 and R0 is equal to n, which means that it is the first and last element in the array. In this case, Alice loses or Bob wins. Okay. And in all the other cases where L0 R0 is not the entire array, or there is no 0 in the element in the array itself, in this case, Alice will win. So a sufficient check to check if Alice can win is either there is no 0 in the array, or uh, all the zeros occur in a subarray other than the array itself, entire array itself. So let's look at the code just quickly. Yeah, so we go to the entire array, and we go to the entire array, and we store the first and last occurrence of the zeros in the array. And if the first and last occurrence are the last if the first and last occurrence of 0 are the first element 0 and last element n minus 1 itself, in that case Bob wins, otherwise Alice will win the game. Great. So now let's move to the second problem. The second problem, it is given us we are given an array of A of length n, an integer k, and we define f of L2R to be the max value of the array subarray L2R, A of L2R. Now we can perform this following operation: n minus k plus 1 times. We select the length of the let current length of the sequence be mod A. So we pick an interval L2R such that of length k such that this interval has a maximum MEX value over all windows size of size k. And once we have the maximum a window of size k from this array, we must delete at least exactly one element from this array, from this window. So for example, if we take this example 1 2 0 1 3 0, it has two possible pairs, L equal to 1 to 3 or L equal to 2 to 4. So we can pick one of these windows and delete an element from this window. So after n minus k plus 1 operations, we are left with a sequence of length k minus 1. Let's find out the maximum possible MEX of the array after all the operations have been performed. So firstly consider what happens is firstly try to focus on this problem, on this sub problem. What is the maximum MEX of a subsequence of length k minus 1? First try to focus on how we can solve this question, right? So for this, basically the maximum the actual maximum value is length k MEX equal to k if uh, all values from 0 to k minus 1 occur in the subsequence b, right? If all the values from 0 to k minus 1 occur in the subsequence, then the MEX is k. Otherwise, MEX is x less than k if x does not, if 0 to x minus 1 belongs to a subsequence. Okay. So we can just do a very simple check on this array. We can just store all the values from 0 to k minus 1 in the array A itself. And so if you have like a frequency array, say, of the entire array A, and we can just go through this, we can compute this frequency array and go and find a mix for a subsequence of length k minus 1. Now we'll make a claim that this um, maximum subsequence of length k minus 1 is the answer itself. And to see why that happens, observe what we are doing in the operation. We pick a window or a subarray of length k, and we remove uh, some AI belongs to A of L to L plus k minus 1, right? The k size window. Now, if we observe carefully, what we have to do simply is to reach this final MEX is to uh, pick an element from this window which does not occur in the final MEX. Let's call this final MEX B, right? B of 0 to k minus 1. This is the final MEX we're targeting. 0 to k minus 2 because its length is k minus 1, so 0 to k minus 2. Just the max MEX, right? So since so remove AI which does not belong to the final MEX P, final subsequence P, and we'll always have this this choice because we have a subarray of length k and the subsequence targeting which we're targeting of length k minus 1. So there has to be right. So our B has length k minus 1 and A of L2R has length k, right? So it is one extra length for this array A. So there must exist some AI belong to A of L2R which does not belong to B because it has one extra element. So we can just solve, what we can do is we can just repeatedly do this in, operation. We'll first compute the maximum MEX, right? And once we have that, we can reach this because we can always pick an element from the window of size k, which does not belongs to the final maximum subsequence. So the answer is just the maximum subsequence, maximum MEX of a subsequence of length k minus 1. So if you look at the code for this question, uh, yeah. So what we do is we uh, just build a frequency array for this from 0 to k minus 1, and then find the maximum MEX for subsequence of size k minus 1 using this frequency array. And this is the answer itself. So it's a very simple question. If you can make the observations like I mentioned here, it is quite easy to solve. Great. So now let's try problem C. For problem C, what we're given is we have n bases in a line, the kth being the home base, and initially there are only use a single soldier at base k, and each data following happens in any order. We give out an order choosing a base I and any number of soldiers inside that base, and we choose any number of soldiers inside that base, and we tell all the soldiers to move to base I plus 1 or I minus 1. And in each day, a new soldier enters the home base key. So we have to find the maximum number of bases at the after m days, which are 45. And by 45 here it means that there is at least one soldier in the base. So we have to find a maximum number of bases after m days, and on each m day we can uh, move soldiers from one base to the adjacent base, and add a new soldier to the kth base. So for this question, think about how we can, let's say if you consider some good samples here. Let's consider this sample 774, n equals 7, m equals 7, and k equals 4. So initial setting something like this: 0, 0, 0. Third element is a home base, so it has one soldier, and again 0, 0, 0. So k is equal to 4 is a home base and it has one soldier. The remaining are empty. Now, suppose we want to fill these two bases to the left. First, we will store uh, two soldiers in the home base, so we need one extra day for this, right? 2, 0, 0, 0. This is after day 1. After day 2, we give an order to move all soldiers to the left base, right? So this is 0, 0, 2. We move 2 here, and one extra arrives here, and it becomes like this. And finally, we give order for one soldier to move to this uh, left base again from this third to second base. So 1, 1, 2, 0, 0, 0. Okay, so this took a total of 3 days to move soldiers 2 positions to the left. Now, if you've done say 3 positions, say, it would take 0, 0, 0, 1, 0, 0, 0. First, we will spend 2 days to accumulate 3 soldiers in the home base. So 0, 0, 0, 3, 0, 0, 0. And then we'll gradually move all the soldiers to the left direction. So 0, 0, 0, 0, 0, 0. And then 1, 1, 1, 3, 0, 0, 0. This takes 5 days, right, to cover 3 positions to the left of the home base. In general, we accumulate, if we want to cover x positions to the left, we accumulate soldiers at the home base. Uh, we accumulate soldiers at home for uh, x minus 1 days, because we already have 1 soldier at the home, so we need x minus 1 days to accumulate x soldiers at the home base, and then x days, and then to spread the soldiers to x positions, to x positions to the left, we need x days. As we are gradually, as in each day, we are moving the soldiers 1 position further to the left. So total, to cover x positions to the left, we take 2x minus 1 days. Okay. Now, if you consider this example again, after 5 days, we are left with something like this: 1, 1, 1, 3, 0, 0, 0. Now we have 2 more days remaining, since we have a total of 7 days here, right? We have 2 more days remaining, so we can build it further. Suppose 1, 1, 1, 1, 3, 0, 0. This is day 6, and 1, 1, 1, 1, 1, 2, 0. This is day 7. So we end up with answer of 1, 2, 3, 4, 5, 6, 645 bases. So basically what happened here is, we in the time we were spreading our soldiers to x positions left, in the x days, we built up another x soldiers at the home. So we spread out this x soldiers over the remaining days. So suppose we accumulate so firstly, for x positions to the left, right, we require 2x minus 1 days, and for remaining right positions, we can either cover x positions, because we have we've been left with X soldiers here while shifting our soldiers to the left. So we can move this X soldiers to the right, or M soldiers, or or M's positions, or not M position, M minus 2x minus 1. So if we have very few days remaining, in this case, you have only 2 days remaining. So even though we had 3 soldiers here, you can only cover 2 positions because you had 2 days remaining. So M minus 2x minus 1, 2x minus 1, which is the remaining days. All the remaining slots actually present here. So we will uh, brute force over the left positions we will be covering. For x left positions, we require 2x minus 1 days, and for the remaining days, based on the number of uh, soldiers we have left, and the number of days and slots we have the right of the remaining, and the number of slots we have remaining on the right of the base K, we will spread out the remaining soldiers to the right. And we can also flip this condition. So we will first do x positions to the right, and then remaining soldiers to the left of the base. So we can flip it as well. So this is just a solution for the problem. Now, if you look at the code real quickly, uh, yeah. So like I discussed, I first check through each uh, left position. So firstly, k minus 1, I'm just covering k minus 1, then k minus 2, k minus 1, then k minus 3, k minus 2, k minus 1. So I'm increasing the slots on the left hand side. I'm covering for uh, for x class, I look at 2x minus 1 days, and for the remaining day, so m minus past days, I cover the right positions based on this 3 minimum values. So either I spend all the remaining days, or I cover all the slots to the right, or I use up all the remaining soldiers in minus k. So the answer is simply this covered slots plus the one extra base slot, which will always be covered. Similarly, I can do the same thing for the other way around. So cover the right positions up to X position, and then spread out the remaining soldiers to the left. So we can just brute force over this and take the maximum answer we have found. Now for the problem D, it is given that you have a rooted tree of n vertices from number 1 to n, and the root index has vertex 1, and each vertex is essentially white. Now we can color the vertices black based on this. Select a subset S of white vertices such that no two nodes in S are connected by edge, so they are not adjacent. There's no adjacent edge, and uh, they don't have the same distance from node 1. If you consider the example, 1, 2, 2, 4. Let's take this one. 1, 2, 2, 5, 2, 4, 2, 3. So this is something like this. Uh, 1, 2, 2, 3, 4, 5. So firstly, we know that we cannot take any elements which are the same distance from 1. So this is basically saying that for a subset S, uh, no two elements nodes in the same level, because if they are the same level, they're the same distance from the node 1 or the root node, and uh, no two adjacent nodes. So this basically means that if you have if you have a node represent in the array, like if you have 2 in the array, we cannot take any of its children or its parent. Okay. So firstly, since we cannot take, if we have, say, we require uh, mx operations to complete this, to complete our array, right? So firstly, since we cannot take any elements from the same level, our x must be greater than equal to max level of I. Here level of I is the number of elements in the ith level. So x is greater than equal to max level of I, right? Also, we know that if we take a parent element, uh, or if we take uh, say a node like 2 here, we cannot take any of its children in the same operation. So x is greater than equal to max of child of I. This is the number of children for the ith node. Okay, so we can easily compute both these values, the number of nodes in the ith level, the number of children for the ith node in a single DFS operation, a DFS algorithm, and we will uh, basically take the maximum between these two as the answer. And this is sufficient because it ensures that in any of the operations, both, because this operation, this condition is satisfied this by this inequality, and this inequality in this condition is satisfied by this inequality. So if both these conditions are met, our answer will be satisfied. So if you look at the code quickly, uh, right. So firstly, we perform a DFS operation to calculate the depth, not depth, the depth count, which is the number of nodes at the ith depth, and the we also have the adjacency list, which we can use to find the number of children. So we perform a DFS to find out the number of nodes in each layer and the each layer, and then we go through each array. And what we do is firstly, uh, size of adjacent of 1 into 1 allele. This is the number of child number of nodes adjacent to I. So just to make a quick correction to this, it should be 1, right? This should be 1 because uh, we have to, if we have 3 different uh, children, right? We must first have 4 different operations. One operation to take the node 2, and then the parent node, and then one operation for a single child node. So 3, 4, 5. So actually, max child of 5 plus 1. Okay. So we take the entire adjacent array. This is the and for the adjacent array, we know that in this list, you also have the parent element. So number of childs is at this size of this list -1 and +1 for the current node, like I discussed earlier, child plus I. So it is adjacent of I +1 into this thing itself, adjacent of I, and also maximum of the ith number of nodes in the ith depth, so depth count of 5. And finally, for the node 1, we know there is no parent for the node 1. So number of parents, number of children for the first node is adjacent of 1 itself. So we do size of adjacent of 1 plus 1. And this gives us the final size of the final number of operations we need to color all the nodes. Now, if you look at the uh, second part of this problem, D2, this is the same thing, but we have to now find a way to color all the nodes itself. So we have to find the x operations, and in each x operation we'll put a set from the tree such that all sets are white, all the numbers nodes in the set are white, and they meet these two uh, conditions we discussed earlier. So we'll use sort of a coloring approach to do this. So suppose we declare a color for each node, color of I equal to y implies we uh, paint I in the white operation. So if we can paint each color of I in some color from 1 to x, where x is the number of new number of operations, we will solve this problem. Okay. So for this, we will paint it like this. So if you consider this example itself, like 1, 2, 3, 4, 5. Now the minimum operation for this is 3, 3, 3 is 3. If it is no 3, it is okay. Sorry, it's 4. Sorry, because uh, for this node, you have 3 children plus 1 node for this, so 4. Yeah. So you have to paint the nodes in colors from 1 to 4. So let's suppose we paint. So we go level by level. So for the first level, we paint the nodes in increasing order from 1. Now for second node, for the level 2, we see that we cannot paint in the color 1 because the parent has color 1. So we paint it in color 2. Now again, we go to the next level. We start from the color 1. So we paint this with 1. Then the next color is 2, but the parent already has color 2. So we use 3. And finally for this 4. Okay. So this is one way to color the entire array or entire tree. Now if we consider a better example, let's see. Hmm, let's take this one big example. Let's say 1, 2, 2, 3, 1, 2, 2, 3, 2, 4, 5, 1, 2, 2, 3. Sorry, 1, 2, 2, 3, 4, 2, 5, 4, 6, 3. 4, 2, 5, 4, 6, 3. I think it's 7, 7, 1, 7, 8, 5, 9, 6. 1, 7, 8, 5, 9, 6, and 10, 4, 11, 7, 12, 8, 13, 10. 10, 4, 11, 7, 11, 7, 12, 8, 13, 10. 12, 8, 13, 13, 10. Now for this, the next question is firstly for the level count. There's 1 here, 2 in this level, 3 in this level, 3, 3, 3. So either 3 or if you got a child, first one has 2 child, so 3. This has 1 child, so 2. 2 has 2 child, so 3. And the maximum child count is 3 itself, so 2 itself. So it is also 3. So then maximum minimum number of operations is 3. Okay. Now if you have to, if you paint this, I'll do one thing. I will go through each level one by one, and then paint it starting from 1 itself. Suppose I paint this one, then this 1, 2, then 1, 2, sorry, 1, 2, 3, 1, 2, 3, 4, sorry, okay, 1, 2, 3, 1, 2, 3, and then 1. Okay. Now, if we do it as a griddly like this, we'll see there are many problems. Firstly, the main problem here is that uh, for the bunch of nodes, or for almost all nodes, the parent and child have the same color. So we cannot do it like this, right? Uh, so one optimization we can do to improve this is to flip the ordering of our colors in every turn. So basically what I mean is, if we go back to this first case, firstly you're painting it from left to right, right? Now we paint it from right to left. So 1, 2, 3, and then again from this other 1, 2, 3, and again right to left, 1, 2, 3, and then 1 here. Okay, so now we still have some conflicts, like here is, for example, and also there's one conflict here as well, right? So there's still some conflicts, but it is much better compared to earlier. So by doing a sort of zigzag coloring, we have sort of somewhat good coloring. Now to resolve these conflicts, there is one way we can do it. Suppose we have in a level, we have two conflicts, right? Something like, let's say we have 1, 2, 3, let's say like this, right? 4, 5. Suppose it was something like this, okay? 2, 3. Okay, let's say it something like this, okay? If you have two conflicts, we can just swap these two colors, right? Because uh, there can only be uh, in each parent-child section, or if in each parent-child uh, uh, in each this sort of portion, there can only be one conflict, which is between the parent and child. So if we uh, have two conflicts here, we can just swap these two nodes colors, because we know that these two parents have different colors. So if we swap these two colors, the conflict will be resolved. So in this case, uh, we can just swap these two colors to resolve our conflict. So basically, as we are painting the each level, if we face any conflict, we store it in an array, and then in the end, if we have like two conflicts or four conflicts, we can just and swap them and resolve the conflicts. But it can also happen something like this, say, where we are left if you have an odd number of conflicts. So something like let's say 1 and 2, 1, 2, 3, 4, 5, let's say we're having 1, 2, 3, right? Let's say we have let's say we have something like this as well. 6, 3. Okay. Now let's say we do something like this. Okay. 3, 4, 5, 6, 7. So first we go like this, and for the third level we go like this: 1, 2, 3, 4. In this case, there's just one conflict in there between these two, right? But uh, since there's only one conflict, we cannot swap it with anything. So we will have to brute force for the entire level to find out if there's a possible node in this level can swap the color with to solve a conflict. For example, in this case, we can swap between these two because this parent has color 3, so you can use color 2 here, and you can resolve the conflict. So we will paint it this 3, paint this 1, and paint this 2, and resolve a conflict. Now it may also happen that uh, there is no possible way to resolve the conflict with any of the colors, with any swaps. For example, the very simple case in this here. In this case, I painted this first level with 1 and 2 color like this, but the parent there's only one parent root node with color 1. So regardless of how I sort of uh, regardless of how I paint how I swap these levels in this first level, I cannot remove this one color from this level. So I'm forced to increment this color to a new color. So to summarize the entire algorithm, firstly, color each level in zigzag order, right? Two, if multiple color conflicts in a level, color conflicts, swap the colors. If only one conflict, bru- uh, find a swappable node like I discussed here. We can just iterate through each node on the level and find if you can find a swap here. Otherwise, if we cannot find a possible swap in the level, we increment it. Right. So if we do it like this in a sort of greedy way, we can color all our nodes using X colors. So if we just want to show this on this tree properly, so that we can get a good idea the algorithm. So do something like this. Right? Uh, then right? Okay. So firstly, for the root node, we color 1, 1 here, and we color 1, 2 in this left-right fashion. We said this here, there's a conflict between these two, but there's no swappable node in this level. So we uh, increment this. Now again, right to left fashion is zigzag order. We do it like this. We see that there are two conflicts between these two nodes, so we swap them like this, like this. Right. Again in the left-right fashion. 1, 2, 3. In this case, it is perfect from the start. There is no conflict, so it's good. Again, in the reverse order, 1, 2, 3. The conflict in these two nodes. We find a swappable node in this level. Since there's only one conflict, we have to find the swap manually. We see that we can swap it between these two. So this becomes 3 and this becomes 2. And finally, we paint this single node in the bottom here. So we have successfully painted the entire array with 3 colors. And now what we'll do is for the operations, we can just find a number of nodes for each color and paint these 3 color nodes separately, 3 sets separately. So if you look at the operation now, firstly in the DFS operation, I'm storing the number of nodes, number of the nodes in each level separately, and coloring the parent for each node, like so. Now I'm going to each level, on the second level, and then as I mentioned, I'm starting from color 1. I color each node in increasing order from 1 to C, 1 to X. And if while coloring I face any conflict between the current color and parent's color, I store the conflict in the array. Now, if there are more than one conflict, I can swap the conflicts to resolve the conflicts. Otherwise, if there is one conflict remaining, that is, this number of conflicts is odd. In this case, I can brute force through the entire level to find a good swap for this to resolve this conflict. Otherwise, uh, I'm forced to increment. So I'm supposed to use the next color to color this node, right? So if we have found a swap the two colors. Otherwise, we have to increment the color. Okay, so if we do that, we have all the colors ready, and we can just store the colored nodes separately in a set, in an array, and then paint all this arrays to get the final answer. Great. So now for the last question for today, we will seeing problem E. Now for problem E, an array like this, or array is considered good if it is strictly decreasing and strictly increasing, and this equation we have 1 by LCM A1 A2 1 by LCM A2 A3, this summation is greater than or equal to 1. Okay, so let's write this properly here. So we know that for given A, also basically what we have to do here is we can replace all zeros in A with integers from 1 to m, and you have to find number of ways to replace these zeros so that the array A remains good. So given A, you have to make it increasing, strictly increasing, and also 1 by LCM A1 A2 plus 1 by LCM A2 A3 plus 1 by LCM AN minus 1 AN and 1 by LCM AN A1 is equal to 1, right? If you consider a single term 1 by LCM, if you consider firstly, if you consider two different elements, adjacent elements AI plus 1 and AI minus 1, if you consider their subtraction, right? 1 by AI minus 1 by AI minus 1, this gives something like D by LCM of AI comma AI plus 1, right? So this is less than equal to 1 by LCM of AI plus 1 because D has to be greater than or equal to 1, right? We have this equation. So essentially 1 by LCM AI by AI plus 1 is less than equal to 1 by AI minus 1 by AI plus 1. Okay. So if we consider the summation over this entire thing, we get summation I equal to 1 to n minus 1 1 by LCM AI uh, AI plus 1 less than equal to uh, 1 by A1 minus 1 by A2 plus for the first term 1 by A2 minus 1 by A3 for the second term. Then it will keep going like this 1 by A n minus 2 minus 1 by n minus 1 for the second term for the last term 1 by A minus 1 minus 1 by A n. Now if you can see carefully what is happening here, this is a telescoping sum. So what this means is you can cancel out all the terms from this series. So A2 gets cancelled like this, and similarly we'll have a term here like the A3 minus 1 by A4. So it will cancel out as well. A4 will get cancelled as well. So it will keep getting cancelled out until like this, and you're left with the last term and first term. So essentially 1 by A1 minus 1 by AN. Now observe that uh, uh, observe that we have another extra term which we left behind here, which is 1 by LCM of AN and A1, right? So we add this, we know that if we add this to the series as well, and we know that this is less than equal to 1 by AN. Okay. Why is this true? Because we know that LCM of AN comma A1 has to be greater than equal to AN, right? So that from there we can get this inequation. So the final uh, summation becomes 1 by AI 1 by LCM of AI plus 1 plus 1 by LCM of A AN A1 is less than equal to 1 by A1 minus 1 by AN plus this 1 by n term for this. So these two get cancelled out as well. So we are just left with uh, 1 by A1. I know a summation of the value is greater than equal to, must be 1. So also we know that summation is less than equal to 1 by a1, right? So from here we can uh, uh, confidently say that a1 has to be equal to 1 for this summations to hold true. And in fact, a simply becomes 1. Okay. So we are taking the absolute maximum value, which is for this summation, which is 1. Now, if you take the maximum value, uh, absolute maximum value for this sum, then it must hold that 1 by LCM of AI and AI plus 1 must be equal to 1 by AI minus 1 by AI plus 1, because since you're taking the absolute maximum value for this sum, each term mentioned like here like this should also be maximum. So it has, these two have to be equal for this sum to be 1. Now if we think about uh, if we go over this a bit, right, so we can rewrite this as AI into AI plus 1 by GCD of AI comma AI plus 1, right? Because the LCM is nothing but the multiplication of the two numbers by the GCD, right? And this term is this, and this term you can just subtract it like as usual. This becomes AI plus 1 minus AI. From this we get that GCD of AI and AI plus 1 is equal to their difference. Okay, she found a pretty good relation between the two adjacent elements. So we can rewrite this as something like this: AI plus 1 is equal to AI plus K, given K divides AI, right? And this is basically K staticity here. So given any AI, we can pick AI plus 1 like this. So we'll compute all the divisors for K, all the divisors for AI, and we'll have these different values for AI plus 1. So suppose we declare DP state like this: DP of I comma j, which essentially gives a number of ways to pick the prefix a1 to I with uh, AI equal to j, right? This is nothing but dp of I of j equal to summation of dp of uh, j dash dp of I minus 1 j dash uh, given there exists some k such that j plus j dash plus k is equal to j, and k divides j dash. The condition I mentioned earlier, right? So we can transition from AI to AI plus 1. So you can just compute the divisors from for each integer from 1 to m, and you can use this to find if you can transition from j dash to j like this. And using this, you can just easily compute this DP relation. Okay. So if you look at this code real quick, uh, yeah. So firstly, I compute the divisors for each number from 1 to m separately. Then I go through the actual solution. I input the array, and if the array is some value other than 1, it is not possible because I discussed earlier that the array first element must be 1. So if it is 1, then we compute a DP. I go from each position from 2 to n, so in increasing order, and then I go through the previous value j dash, so DP of I minus 1 j dash, and then I go through each divisor of this j dash. So my next value j is previous plus this divisor value, right? So firstly, if this ith element is already fixed, we check if this next value and I value is same or not. If it is not same, continue. Otherwise, we can add dp of I minus 1 previous to this dp of I next value. Okay, so this is a relation I discussed earlier. I'm using the divisors of each number to quickly find out the each sort of appropriate value from previous to next. And once this is done, uh, we can add up the summation. I find the answer by adding up the value for each possible value of the last element n, like this. So this gives us the final answer. So that is all for today. I hope you liked all the problems. This was a very interesting contest and it's a lot of challenging questions to solve. So I hope you enjoyed the explanation. Uh, if you liked it, please do like and comment on this video, and make sure to check out the website for Kepler. You can find the notes for this video on the website as well as some other resources. So see you in the next video. Goodbye.